All right, today we're going full-on detective. We are hunting for a ghost in the machine, a little phantom that makes even the most powerful AI act in ways it just shouldn't.
So, you've probably run into this yourself. You're trying to get a consistent answer from a large language model. So, you do the obvious thing. You crank the temperature, or the creativity, all the way down to 0. That should make its choices completely deterministic, right? 1 + 1 = 2 every single time. But it doesn't. And the reason why is actually way more fascinating than you might think. Our investigation kicks off with a really simple example.
So let's say you use the exact same prompt, same model, temperature locked at 0. One time, it might tell you, Richard Feynman was born in Queens, New York. The next time, New York City. Now look, both of those are correct, but they are different. This isn't creativity. This is something else, something happening way down in the guts of the machine. And this isn't just a rare little glitch. Get this. Researchers at the Thinking Machines Lab ran the exact same prompt 1,000 times and got 80 unique answers. 80, all from a process that was supposed to be perfectly repeatable. So what on earth is going on here? Okay, every good mystery has a usual suspect, and in this case, it's an explanation you've probably heard thrown around online. Is this idea that, GPUs are these massively parallel beasts. They're running thousands of calculations all at the same time. And because the exact order that those calculations finish can change by a few nanoseconds, the final answer gets tweaked just a tiny bit. Sounds pretty plausible, right? And the deep mathematical reason for this is something called floating point non-associativity. Now, back in school, we all learned that adding A plus B and then adding C is the same as adding B plus C and then adding A. The order doesn't matter. But for computers dealing with decimal points, it's not always true. Because of rounding errors, the order of operations can literally change the final answer. And check this out. If you add a tiny number to a gigantic one, the computer has to round off, and the tiny number basically just vanishes. But if you do the math on the two huge numbers first, they cancel each other out perfectly, and the tiny number survives. We're talking same numbers, same operations, just a different order, and a completely different answer. So, case closed, right? Parallel processing shuffles the math, we get different results. But not so fast. Here comes the plot twist. If that theory was the whole story, then shouldn't every single parallel calculation on a GPU be just as unpredictable? And this is where that whole theory kind of falls apart. Researchers ran a basic matrix multiplication, which is like a core building block of how these models think, on a GPU over and over again. And the result? It was bit for bit identical, every single time. So our usual suspect? It has an alibi. It can't be the only thing causing the problem. So this leaves us with a genuine puzzle, a real head-scratcher. We've got these 4 facts that all seem to contradict each other. Some operations on the GPU are random, sure, but the specific ones an LLM uses to generate an answer are totally deterministic. So the server's whole process, given the exact same inputs, should be deterministic. And yet for you, the person typing in the prompt, the result is still random. How is that even possible? To solve this mystery, we have to zoom out. We have to stop looking at a single calculation and start looking at how these massive AI servers handle thousands of requests all at once. Because the real culprit is something called batching. Now, to get this, we need to talk about an idea called batch-invariance. It's a really simple principle. The answer to your question shouldn't depend on how many other people are hitting the server at the exact same time. But it turns out, for most AI models, it absolutely does. Think about it like a delivery van. If that van is only delivering your package, it's going to take a direct, super predictable route right to your house. But that's not efficient. So to save time, the server bundles your requests with a bunch of others into a batch, kind of like loading a whole truck full of packages. Now, the driver optimizes the route for the entire truckload, and suddenly the specific path and the timing for your individual package completely changes. And right here is the smoking gun. The researchers ran the exact same input through the model twice, once all by itself, the second time as part of a bigger batch. Logically, the math for that one specific input should be identical, but just look at the difference in the output. It's enormous. The GPU's kernel, the low-level code, is choosing a different, more efficient way to do the math for the bigger batch, and that changes all those little floating point calculations. So this is it. This is the crucial point. The ghost in the machine isn't just some random quirk in the math. It's the server's workload. From your perspective, the number of other people using the service at any given second is totally random. That randomness changes the batch size from moment to moment, and that changing batch size forces the GPU to use slightly different math, which leads to your slightly different answers. Mystery solved.
So, okay, now we've unmasked the culprit, but how do we actually catch it? How do we force the AI to give us the same answer every single time? Well, the researchers at Thinking Machines did exactly that. They went in and they identified the 3 specific operations that were causing all the trouble. Then they rewrote the low-level code for each one, basically forcing them to use the exact same calculation method, the same order of operations, whether the batch size was 1 or 1,000. Yeah, it's a little less efficient sometimes, but it guarantees perfect consistency. Now, you might be thinking, okay, that's a really cool technical puzzle, but who really cares if my bioassignment says Queens or New York City? Well, it turns out that achieving this level of precision, this perfect reproducibility, unlocks a whole new frontier in AI research. See, it makes something called true on-policy reinforcement learning possible. Now, this is a method for training AIs where it is absolutely fundamentally critical that the version of the model that's out there gathering new data is bitwise identical to the model that's learning from that data. Even the tiniest difference can send the entire training process completely off the rails. And the impact is just crystal clear. With the standard methods, the sampler model and the trainer model slowly drift apart, making the training unstable. But with these new deterministic fixes, that divergence drops to 0. The training becomes perfectly, beautifully stable. The difference between the 2 models becomes 0, perfect alignment. This is the kind of solid, reproducible bedrock that real science is built on. And this really gets to the spirit of the whole project. You know, it's so easy to just shrug and accept these little glitches as just part of the deal with complex systems. But as Horace Ye and his team show, we don't have to accept that. We can actually dig in, understand these systems from top to bottom, and engineer the exact behavior that we want. And that leaves us with a final, really important question. Getting the same answer twice might seem like a small thing, but it's really about control and precision and reliability. So as we continue to build these incredibly powerful tools, what other impossible problems could we solve just by demanding this level of scientific rigor? What else can we achieve when we finally truly defeat the ghost in the machine?